Okay, so last time we talked about polar coordinates, and we're going to go on now and talk about cylindrical coordinates. This one's actually pretty quick because it's pretty much polar coordinates. It's just polar coordinates in space in the sense that x and y, just polar coordinates. It's the exact same polar coordinates, right? And then we have to recognize, because we're in space, there's also the little matter of what is the z coordinate, and so whatever that z value is, that's the third coordinate. So oddly, z is a coordinate both for the rectangular coordinate system and the cylindrical coordinate system. Same z. Right? So because so much is the same as polar coordinates, we get a lot of familiar relationships between the various variables, and so all that stuff comes along free for the ride from previous discussions. Okay, a couple of quick examples. This equation right here gives you a cylinder. Easy way to see that is that you can think of r in cylindrical coordinates not being as distance from the origin, but it's distance from the z-axis. Right? And you think geometrically, looking at all points that are a given fixed distance from the z-axis is going to give you a cylinder. And by the way, thus the name cylindrical coordinates. Spheres turn out pretty well. Keep in mind that we already know a relationship between x, y, and r. And so the typical rectangular equation for a sphere turns into this cylindrical equation for the sphere. Right there. All right. And then I like this next example quite a bit because it's a little bit... It addresses something that students are sometimes a little sloppy about, and that again is the R and what the rules are with R. R is allowed to be negative. Keep that in mind. Right? So if we write this down, Z equals KR, how are we going to deal with that? And by the way, of course, notice if Z is negative, then R is going to be negative, assuming K is positive. Okay. All right, so how to view this? How do I turn this equation into this picture? And there's a really nice move I like to pull here, and that is to notice that in this equation, there's no thetas in there, right? We've got cylindrical variables R and Z, and there's no thetas. So when there's no thetas, what that means is the cross-section in every theta plane, all these cross-sections are the same. Right? You change the value of theta, well, okay, well, so what? Doesn't affect the equation at all. So those cross-sections are all the same. So said differently, if I understand what the cross-section looks like in any one of these cross-sections, then I understand all of them, and furthermore, I would just kind of rotate it around to get the whole, because all those cross-sections look the same. And if you want to know what a cross-section looks like, well, that's actually pretty easy to address. Let's just look in the, what I like to call the ZR plane. In other words, when you're looking at one of those theta cross-sections, as you go away from the z-axis, you're going in the r direction, what you might call the r direction. And this is a really easy line to draw, and then you just imagine what happens when you rotate that line around the z-axis, and well, it generates that cone. Everybody happy? Questions? Okay. All right, so that's all I'm going to say about cylindrical coordinates. You know what? A real quick warning. This is just annoyance, but in high school geometry classes, very often if you have something round, circle, sphere, cylinder, something like that, very often the radius of that round thing, they'll use the letter R to represent, a fixed value representing the radius of that thing. We can't do that anymore because now R is no longer unused. Now R is a variable, right? It's the cylindrical variable. So you can't use R to represent a constant radius any more than you can use X to represent a distance, like some constant distance. No, X is a variable. Yeah, you can't it'd be a confusion of variables if you use x to represent both a fixed distance and also a rectangular coordinate. So same deal here. So just don't use r. Now what you can do, and this is no problem at all, you can use capital R. No problem at all. Right? Or you could do like R naught. Also perfectly fine. Any sort of modified, you could R star or something like that. But you can't use just R by itself. Okay, moving along to spherical coordinates. Flashing back real quick, I observed that some people like to think of cylindrical coordinates as being polar coordinates in space, right? And I think that's reasonable. Unfortunately, some people like to think of spherical coordinates as being polar coordinates in space. I think that's a lot harder to justify. For one thing, it's got significant differences from polar coordinates. For another thing, we already have a polar coordinates in space. That's cylindrical coordinates. Right? So I strongly urge you away from this point of view that, spherical is just polar coordinates in space. That's counterproductive point of view, I think. Okay, so let me tell you what spherical coordinates are. The variables are these right here, rho, phi, and theta. I'm going to describe them in sort of the opposite order. Just kind of geometrically works out better this way, in my opinion. And here we go. Theta, think of a half plane hinged on the z-axis that contains the point you're interested in. So let's suppose, for example, we're trying to describe this point right here. All right, well, that point is going to be in a half plane hinged on the z-axis, and we can talk about that angle, measured counterclockwise from the positive part of the x-axis, the angle that it takes to get to that half plane. All right, how are we doing? Okay, notice theta, familiar. It's the exact same as the cylindrical theta. Nice. Okay, next, phi is measured off of the positive part of the z-axis. It's measured parallel to this plane, parallel to this what I call theta plane, with the understanding that the positive direction for the angle is positive, toward the theta half plane, and negative values would be away from the defined half plane. Okay. All right. So that's phi. Notice that between the two of them, phi and theta, that defines a direction. Right? If you know phi and you know theta, that defines a direction emanating out of the origin, and in that direction, you can then talk about. And I'm going to have to do the usual air quotes, how far you go in that direction. Of course, there is the possibility that this rho might be negative, in which case just go the opposite direction. So with that disclaimer, it's, how far you go in the yellow defined direction. And with those coordinates all known, notice that gets you to your point. All right, so these are our three spherical variables. Everybody see the picture there? Okay. All right, now, again, geometrically, as it turns out, it's easier to think of theta first, but in practice, people tend to write rho, phi, theta, and they put the theta last. I will confess, I think that's weird, and yet I don't want to say standard, but it's extremely common as it approaches standard. It's almost always written in this order. Okay. All right, so we have spherical coordinates. What's the relationship to rectangular coordinates? What we're going to do is we're going to focus on this triangle right here. And it's a little bit hard to look at that triangle because we're looking at it at a kind of an angle, and it can be confusing. So what I like to do is just redraw that triangle exact same triangle. I'm just looking at it head on here. If I can get that to it. Like that. Right, little right triangle. And notice that R is one of the sides of this triangle. Notice that phi is that angle right there, which means it is also that angle right there. And a little bit of easy trig gives you this formula: R is equal to rho sine phi. Now, case could be made. Who cares? Why do we care about what R is? R is not one of the spherical coordinates. True. But R is related to some pre-existing formulas that we already have. So, for example, we already know that X is R cosine theta. Right? So knowing how to write R in spherical coordinates helps us write X and Y. Oh, man. R cosine theta and R sine theta in spherical coordinates. Everybody see how that works? There's a pretty easy little argument there. Yeah.
So in this case, R is the radius.
R is the cylindrical coordinate. R. Yeah, I hesitate to call it a radius because when you say, as soon as you say radius, that means a distance and that means positive, and I don't want to make such a thing. But better, I think, to view R as just being the cylindrical variable. Okay. All right, and now, of course, we can also look at this other side of this triangle. We can look at this side of that triangle, observe that, well, that's just Z. And Z, of course, is our remaining rectangular variable. So here you go. Here's our relationships between rectangular coordinates and spherical coordinates. And you can look at this and feel like, well, that's a lot to memorize. I'll point out that about half of what we have here is stuff you've already memorized. You've already memorized that X is R cosine theta, Y is R sine theta. That's the same, right? So there's really only two new things to note here, two new things to remember, and those two new things to remember come straight out of this easy little trig argument with this one triangle. So for whatever it's worth, in my life I have never memorized these formulas, ever, not even once. I don't trust myself to remember it. I'm quite sure that if my ability to access these formulas was dependent on my memory, at some point I would absolutely get it wrong. I'm just sure of it. But I'm really good at trig, right? And it's an easy triangle to remember. And if you just think about that picture in relation to this picture, the critical ingredients that you need are right there, and everything else you just assemble. So, for your consideration, I encourage. I don't want to go so far as to say I don't want you to memorize these. I suppose you could. Maybe you're better at that than I am, right? But it's certainly not sufficient to only memorize these. Make sure that you understand this argument that gets you there. Alrighty, couple of examples. Sphere. Much easier to write a sphere centered at the origin in spherical coordinates. And again, thus the name. Right? Okay. All right. Let's see here. Here's a tricky example. This is a good mathematical weightlifting. I like to call it a little bit of geometric thinking, gymnastics. So suppose we are considering this point right here. I've drawn a picture of, and how would I write spherical coordinates for that point? Keep in mind, spherical coordinates are not unique. Right? None of these coordinate systems we're talking about are unique. Spherical is the worst one. It has two different angles, and therefore there are two opportunities that you could either be going exactly the right direction or exactly the wrong direction, and therefore altogether there are four equally acceptable, perfectly valid spherical coordinates for a given point. Not just two like there were in polar coordinates. And of course all this is ignoring, the plus 2 pi. You can always add 2 pi to an angle and nothing happens. Okay. So I'm going to walk you through some of this. I'm going to leave some of the details for you all to work out on your own. First, a little bit of geometry. We're given 1, root 3, and 2 as those distances. And you can look at the various little triangles involved here and persuade yourself that these angles are those values, and et cetera with the geometry. And with all that in mind, let's start talking spherical coordinates. So, what's theta for this point? Temptation to say, okay, well, there's the half plane. That corresponds to this angle, which we've already agreed is pi over 3. So shouldn't theta have to be pi over 3? And it may be pi over 3, but don't forget there's also, you can add pi, right? If you do a half turn, adding pi, that gets you around over here to the opposite side, where theta would be 4 pi over 3. Right? Now there's a temptation to say, well, that's pointing the wrong direction. You can't do that. If you use this angle 4 pi over 3, how do you get to the point in question? Well, keep in mind that phi, positive values of phi go that way, and yeah, sure, maybe that looks like you're going the wrong way, but negative values of phi go backwards. And so negative pi over 4. Right? If you're using theta as 4 pi over 3, letting phi be negative pi over 4 points you in the correct direction. Everybody with me? And going, let's see here, with a positive value of phi, there's a positive value of phi. Well, let's see here. What would that be? That is a full pi greater than the negative pi over 4 we were just talking about. So this is 3 pi over 4. Also fine, right? 3 pi over 4. And again, that just gets you pointing in the exact wrong direction. And when you're pointing in the exact wrong direction, you just need for rho to be negative. Everybody see what I'm talking about here? So you've really got 4 different options. So I've deliberately just kind of hit the highlights and drawn just the sort of the sketches. What I want y'all to do is to fill in the blanks and write down all 4 of the spherical coordinates for this point. And again, ignoring 2 pi's, right? 2 pi is boring. Okay. Always works. Okay, so I think it's a really good exercise. Think it through, all 4 different options for this one. Okay. All right. Here's a cool little application. Y'all, I hope, are familiar with longitude and latitude. So east longitude is measured like that, assuming, by the way, that I have the globe here set up in what I'm going to call the usual way, where you put the prime meridian on the positive part of the x-axis, center of the Earth at the origin, of course, North Pole on the z-axis, the usual setup. So east longitude is like that. North latitude is like this. And notice that these have a lot in common with spherical coordinates. In fact, east longitude is exactly theta. That is exactly what theta is with this setup. And now let's see here. Phi, well, okay. Phi it's not exactly the same thing, but notice that phi and north latitude have a strong relationship to each other in that they always add up to pi over 2. Right? The bigger north latitude is, the smaller phi is, and vice versa. And they add up to pi over 2. So with these observations, we have very quick and easy ability to convert points on the surface of the Earth, for which I know longitude and latitude. I can convert those to spherical coordinates with really easy little rules. Notice, of course, by the way, also that the rho for any point on the surface of the Earth is just the radius of the Earth. And it's not exactly a constant, but for ballparking purposes, this is really close approximation. Okay. All right. So what you can do with this is the following really clever argument. Let's ask the question, how far is it from Durham, where we are now, Duke Blue, to, I don't know, whatever city that would be. I don't know if that's Oslo or Moscow or something like that, some city, way off over there. How would you compute that distance? Now notice, hard problem, because you cannot just compute straight line distance. That would tunnel under the surface of the earth, and that's not on the table, right? Do you, kind of go along a latitude line and then up a longitude line? Obviously not. That's clearly not the shortest distance. Is there a Pythagorean relationship here that you can use? Oh, no, definitely not. Right? So, hard problem. How do you compute that distance? So, here's a neat move, and I wish I thought of this, but I didn't. Somebody much more clever than I thought of this. The point is, if you know these longitudes and latitudes, let's see here, I will use the dark blue here. If you know the longitudes and latitudes for these points, easily Googleable longitudes and latitudes, right? Well, per the observations above, you can write those in spherical coordinates. Nothing to it. Once you have the spherical coordinates, you can convert to rectangular coordinates. Formulas on the previous page. Nothing to it. And once you have the x, y, and z coordinates for these points, you can use the standard sort of one of the basic formulas about dot products, and the dot product is the product of the magnitudes. We're on the surface of the earth. The magnitudes are all r, radius of the earth. So dot product is the product of the magnitudes times the cosine of this angle. This is the angle between those two vectors. And then you can solve for that angle, because the dot, you've got the rectangular coordinates. The dot product is easy to compute. A little bit of work, you can solve for that alpha. And once you know that alpha, you can then compute this distance using the old high school geometry formula for an arc length of a circle. Everybody see how that worked? It's very clever. A slick move. All right. Okay. All right, moving along. We saw something like this with polar coordinates. Morally equivalent deal in spherical coordinates. If you want to convert a rectangular equation into a spherical equation, the way you do that is pretty much just plug in the formulas. For example, notice here x. There's our new formula for x in spherical coordinates, rho sine phi cosine theta, otherwise known as r cosine theta. Again, easy to remember if you think of it that way. Do look for opportunities to save yourselves a little trouble. Notice that if you expand out this square, right, and move things around a little bit, then that gives you the opportunity to just notice rho squared right there. And now we just saved ourselves a certain amount of messing around with Pythagorean trig identities. So that was convenient. And then everything else, there's the only thing left to do is to plug in that formula for x, solve for rho, cancel common factors, blah blah, and here's your formula for rho as a function of phi and theta. This is the spherical equation for that sphere. Everybody see how that worked? Bad news. This does not work just, perfectly glass smooth like it did in this case all the time. Do notice that we got really lucky that those canceled. Right? That won't always be the case. So that's the bad news. The good news is I won't ask you to do this in any situation where it doesn't work out pretty nicely. But nevertheless, I think I should, full disclosure, this method runs into some impediments sometimes. Okay. All right, last thing I'm going to say about spherical coordinates and all the coordinate systems is I want to talk about standard basis vectors. So y'all remember the rectangular standard basis vectors. We've talked about those before. And again, standard objects in linear algebra. Take your pick on the notations. I like the E1, E2, E3. Again, you're going to run out of letters if you find yourself doing some economics problem that has 7 variables. The E's are much better. Okay, so a couple of things to say about this. Notice that these vectors are constant. They're always the same, right? Wherever you are in space, the direction in which only x is increasing is always that one. Right? It doesn't matter where you are. Only x is increasing. Boom. That's the vector. Okay. All right. And various other things. Various other nice features that we've already noted. So how do we do that for, let's say, polar coordinates? And so let's suppose, for example, that we are right here. What is the vector that points in the direction where only r is increasing? In other words, theta is constant, only r is increasing. And, well, that vector there, I think you can persuade yourself, is the position vector divided by its own magnitude, because this this needs to be a unit vector. It's a unit vector pointing in the direction of a given vector, and after all, that is one of our PAT concepts, this formula right here. Everybody good? Okay. All right, how to find E theta. Now, this one requires a different argument. How would I find this vector pointing in the direction where only theta is instantaneously increasing and r is instantaneously not changing? Different arguments you could make. Here's my favorite. My favorite is to observe that, if I know ER, then all I really need to do is take ER and rotate counterclockwise a quarter turn. And that rotation turns that vector into that vector. And again, this is a linear algebra thing. I want to remind y'all about how this part of linear algebra works. We make the observation that rotations are linear transformations. Linear transformations are always represented by matrices. Matrices can always be understood by their columns, and those columns are always the images of the standard basis vectors. Right? So, if you want to find this formula here for converting, turning that vector into this vector, view it as a linear transformation, write it as a matrix, look at the columns, think about what happens when you rotate. In this case, we're just doing rotation. So what happens when you rotate standard basis vectors? That'll give you your columns, and then when you multiply accordingly, you'll get that. So I hope everybody is... hope that rings some bells, at least partly. If not, then you want to definitely sit down, take some time, and work it through. Make sure that you can comfortably confirm that this is how you do a 90 degrees counterclockwise rotation. If you get stuck, if you're not sure, I kind of don't remember that stuff, come to office hours. I'll be very happy to explain and elaborate. It should ultimately at least I should be able to persuade you that this is nothing more than an example application of ideas that you should have seen in Math 218. So anyway, please don't just let it sit that you don't know how to do this. I need to make sure that everybody can do this. All right? Is that cool? All right. Cylindrical, like I say, it's a lot like polar. We already have these formulas here for the polar standard basis vectors. Cylindrical is the same thing, just comma 0 at the end for those two. And then, of course, there's the third one, which, of course, is straight up. So, EZ is no problem. Spherical, though, there's some interesting things to talk about. Now, this E theta here is a freebie. That E theta is the same E theta from cylindrical, which, aside from this 0 at the end, is the same E theta from polar. Right? so that's a freebie. This E row, similar trick to ER from polar coordinates. We just realized it's the position vector divided by the magnitude. Points in the same direction as the position vector. So that one, not that bad. And then there really is a clever little move trick here in coming up with E phi. And that is to realize that it's perpendicular to these two, and therefore we can write it down using the cross product. And these are unit vectors, and this angle between orange and green, that angle is a right angle, so that means that the cross product is going to have magnitude 1. And so we don't even have to normalize this. It comes already normalized. And there's your formula for E phi. Everybody follow? Yeah.
What are these vectors representing?
These are what you would call these spherical standard basis vectors. So if you're doing, there's various kind of geometric arguments you might want to make, and you're at this location, and for whatever reason, spherical coordinates is your friend, which is very often the case. And when that's the case, it's nice to have a reference frame, right? A basis that is spherical friendly. And the usual E1 and E2, E3 is not spherical friendly, right? It's not easily relatable to what spherical coordinates are doing, but these are. Yeah.
And they kind of point in different directions depending on where you move your R.
Exactly. Yeah. That's right. So they're let's see here. They're kind of like this for that point, but if I go up, it turns like that, and if I go down, it turns like that, and if I rotate around, then it goes like that. Yeah, totally. Anybody else? Okay, so a couple of warnings. And again, we already talked about this first one. The rectangular standard basis vectors have the nice feature of being constant, and that's a luxury that we don't get with these other coordinate systems. They're just not constants. You can see the formulas. They don't work algebraically nicely with linear combinations. Like the rectangular standard basis vectors, really convenient in that way. And so, for example, coordinates are coefficients in a linear combination. This is awesome for rectangular standard basis vectors. And if you, hopefully write down something along these, sort of seemingly analogous lines, no, crash and burn. It just doesn't work. It's just not true. Okay. All right. There is one piece of good news, and that is that they do happen to be orthogonal. And that's kind of a coincidence. That's a lucky break. But if you look at these formulas and pictures, it's not hard to persuade yourself that they are, in fact, always orthogonal. And that's nice, I suppose. Okay, for whatever it's worth, I'm not going to be doing much with, for example, spherical standard basis vectors in this class. There are some situations where we could, but I'm going to have my own, I think, better ways of thinking about those things. So I'm showing them to you here, not because I'm going to be using them, but I'm showing them to you because someone else in your future may want to use them. Okay, so that does it for Chapter 1. We're moving along now to Chapter 2. The first couple of pages here is largely terminology and setup. So bear with me. This is going to be seemingly boring and, who cares kind of stuff. But we got to get the terms right, and we got to everybody's get on the same page of our fundamental objects. The very first thing I want to talk about is what a function is. This is a very commonly misunderstood point. A function, to a lot of students, a function is a formula. And that's really not good enough. You can get away with that in a lot of instances if, what you're doing doesn't really, not that big, nothing particularly subtle happening. But really doesn't work in certain situations. Very importantly for us going on, a function is a trio. It's three things. All three things are part of what defines what we mean when we say a function. And specifically, the trio is a domain, which is where the inputs to the function come from. A target, which is where the outputs go to. Right? We know that a function takes inputs and gives outputs, right? So if you've got your function here, where the inputs come from, that's called the domain. Where the outputs go to, what the outputs land on, that's the target. And then the third thing is what I'm going to loosely call the formula. Of course, it doesn't always have to be an algebraic formula. Might be something else. I'm going to show you such an example in a minute here. But the rule that tells you, given an input, what is the corresponding output. Whatever that rule is that plays the role of a formula. It's called the rule of assignment. So again, a function is not just one of these things. A function is the trio of all three of these. Yeah, so
is a target the same as like a range?
It's a great question. Tragically, no. Well, it depends on who you ask, because tragically this word range gets used in different ways by different people. So in this class, no, they're different. And I'll get to that in a few minutes. It's a great question, but it's coming up. Yeah. Okay, so let's see some examples. Here's an easy example, natural log. Y'all know that's a function. And the domain I have indicated here, the positive real numbers. The target I'm indicating here as the set of all real numbers. And then the rule of assignment, aka the formula, is just natural log, which is also the name of this function. So the idea is that writing it this way, by the way, when you write down, for example, natural log here, you're saying, okay, here's the name of my function. It's called natural log. The colon says, okay, now, before I go on, let me tell you some important things about this function. And then the important things you need to say are, what's the domain, where are the inputs coming from? What's the target, where are the outputs going to? And the arrow indicating that action of things coming out of the target, out of the domain and going into the target. So this is just notation, but it's pretty standard notation. I'm going to be using it a lot, so be on the lookout for that notation. Okay, now here's my next example. This is the one where we're going to have kind of a weird rule of assignment. This is what I like to call the student ID number rule of assignment. And, well, just take any student on campus, right? You say, hey, what's your ID number? They give you a number. So it's not a formula, but it is a perfectly good rule of assignment. Whoever you ask, for any given student, there is exactly one student ID number. And again, we're talking student ID numbers, not Duke Unique ID numbers or net ID. All the various IDs we have on this ridiculous system. Okay, student ID numbers only. Okay, so here is an example of this thought of as a function. Notice, I have to tell you what the domain is, collection of all students. And I have to tell you what the target is, namely what kinds of things are going to come out of this rule of assignment we have. The values of this function, the output values of this function. What kind of critters are they? Well, they're integers. Right? Okay. Now, here's the thing. A perfectly legitimate alternative way to turn this into a function would be this, which you'll notice. Now, let's compare these two functions. I claim that these are different functions, even though we're defining still for all students, right? Nevertheless, f, as I have it defined, has a target that is z, all integers, and g, as I have it defined, has a different target. And it seems a little silly, but you got to hand it to me that a student ID number is also a real number. In addition to being an integer, is fair to say also it's a real number. So, which one of these is right? Well, they're just different ways of creating a function out of this idea of using student IDs. Okay. So F and G, as I have it defined here, different functions because they have different targets, even though the rule of assignment's exactly the same. All right. Question would naturally come up: who would ever do such a thing? Why would you ever? Right? There's a bunch of real numbers here that we're not going to use at all. Right? So it seems kind of more, I don't know, precise or something to say that, shouldn't the target really be Z? I will point out there's a bunch of integers that are not student ID numbers either. Right? All student ID numbers I think they're all either 6 or 7, maybe 8 digits. Right? There's no student ID numbers that are 428,000 digits. Perfectly acceptable integers, not student ID numbers. So this is awkwardly large also. So, I mean, there's nothing wrong with that. But anyway, my point is neither one of these is necessarily better than the other. Okay, all right. You can also change the domain. I can have, instead of looking at all students at Duke, I could say, well, let's look at just the students that are in this classroom right here, right? Just us right here. Every student in this classroom has a student ID number. And so comparing this and this, F and H, same rule of assignment, same target, different domains. This one's defined for all students. This one's specifically only defined for students in this classroom. Okay. How are we doing? So I know that this comes off as a kind of persnickety, but it ends up mattering, and we're going to see why in a couple of minutes. But anyway, that's what a function is. Now, you asked a question about range. This word range unfortunately gets used for two different things. Sometimes range means how I define it here, namely the image, namely the set of actual things that actually come out of the function. And in other contexts, range is used to be a synonym for target. This is very frustrating. And I'm going to use here what I think is the more standard choice for range. But frankly, I'm in any situation where there is a potential for confusion, I'd try to rather just avoid the term altogether. Right? So I almost exclusively use the term image instead of range. Okay, so let's see an example of what this thing is. What is the image? Here is a perfectly good function. You'll notice domain, target, rule of assignment. That's a function. And let's think now, what are the actual outputs from this function, the squaring function? What actually comes out of there? And it's just non-negative numbers. It's not the entirety of the target, right? The target itself is all of R, includes the negative numbers. So the range here quite a bit smaller than the target. Is that cool? All right. A little bit more terminology, and what are you going to do? These things just have to get said. When you have a function and there's an input to the function and there is an output to the function, that thing that comes out is called the image of the input. It's just terms. It's just words. Phrasing it sort of backwards, if you like. The thing that went in is what we call a pre-image of that output. So here X is the pre-image of Y. Y is the image of X. Does that make sense to everybody? And you do have to be careful with your language here a little bit. Notice I wrote here a pre-image. A function might have, an output value might have multiple pre-images. Think about the x squared function. Right? Looking at this function right here. 25 has two pre-images. 5 and negative 5. Perfectly acceptable, both of them. No problem. Okay, more language. And, oh my gosh, let's try not to get lost in the language here. But there's a couple of features about functions that end up being important to be able to talk about, and we'll even see why they're important on the next page that we're not going to get to today because we have too 2 minutes and 45 seconds left. So let me just define these terms. A function is called onto or surjective if every point in the target has at least one pre-image. In other words, every point in the target gets hit by the function. Or said differently, every point in the target is also in the image. So the image equals the target. And here's an example of what that looks like. Notice every point over here has a pre-image. In fact, some of these points, this point right there has 2 pre-images. No problem, as long as it's at least one. Right, over here, this point here has 1 pre-image. And so every point of the target has, as required, at least 1 pre-image. Okay. All right, now let's talk about injective, aka one-to-one. Here's a picture of an injective function. Every point in the target has at most 1 pre-image. At most 1. So let's think it through with this example here. That point has 1 pre-image. Cool. This point here has 1 pre-image. Cool. This point, 1 pre-image. Cool. And this point has 0 pre-images, which is, as required, no more than 1. So this function passes. This function is injective, aka one-to-one. Some functions are neither, some functions are both. This is neither. You can check through yourself and see, roughly speaking, this point here is why we fail injectivity. And this point here is an example of why we fail surjectivity. So, failure. But some functions are both. And functions that are both are really nice because that means that every point in the target has exactly 1, at least 1 and at most 1, therefore exactly 1 pre-image. And if every point has exactly 1 pre-image, what that exactly 1 pre-image is allows me to define what you might literally call the inverse function. Right, so the function that I had drawn here goes this way, but because every point here has exactly 1 pre-image, I can just turn the arrows all around backwards. That defines a function going that way. So this is what we call an invertible function. Okay, and I'm sure I'm out of time by now. Yeah, okay, perfect timing. Just ended. Okay, we will pick up here on Wednesday. Good to see everybody. See you later, and have a nice day. Oh, and a reminder, if you came in after I did attendance, just come talk to me after class. Do make sure to do so, because otherwise you won't be marked off as present, and there, every little bit counts on grades. See y'all later.